Well, thank you. Naturally, when you hear a title like this, there's two questions that come to mind. What and why? And so what we do concretely is we created an intermediate representation called XCAD that sits between classical sequent calculus and real machine code. And so on the one hand, it is a normal form of typical term assignments for classical sequent calculus. And this is in spirit, it's similar to A and F. And so it inherits the safety properties from a logic, and this makes it a high-level language. On the other hand, it admits a direct and straightforward generation of machine code, which makes it a low-level intermediate representation. And so why do we do this? Our work on effect handlers has led us to the understanding that computation is interaction between a program and its context. And so in a pure program, this interaction is rather trivial. When the program is done, it returns the resulting value to the context, and it does so exactly once. In effectful programs, this interaction is much richer. So think of, for example, exceptions, where the program might either return a value or throw an exception. Or think of generators, where the program yields to the context, but then the context might also resume back to the program, and the two are coroutining. We want to model this interaction both on the type level and on the term level. On the type level, we want to specify a protocol for this interaction that guarantees safety. And on the term level, we want to directly express this interaction without any encodings or runtime system. And we found that classical sequent calculus is just great for this. And so in his paper Untersuchungen über das logische Schließen 1, Gerhard Gensen invented natural deduction, which is a logical system, but then also invented sequent calculus originally as a technical device to state and prove his theorem of cut elimination. And so the paradigmatic rule in this logical system is cut. Now in modern term assignments, this rule looks like this. And there is a bit of notational difference. For example, instead of using an arrow, we use a turnstile for expressing a sequent. And also, instead of putting formulas on the left-hand side and on the right-hand side of the sequent, we tag them with either producer or consumer. We call this the chirality because it is like the handedness, what is left and what is right. And so this cut rule now expresses that a producer and a consumer of the same type tau interact in a cut. And in addition to those, we have right introduction and left introduction rules for logical connectives. So here, for example, we see the logical connective of disjunction, and then we see the two introduction rules. This is just the tagged union, and it is defined by having two injections. And that's a familiar typing rules and term assignments. What is perhaps less familiar is the left introduction rule, which is just a match. And it matches on either the first or the second injection. Now, if you want to have a traditional case statement, what we would do is we have a cut between a producer and such a match. On the other hand, we have conjunction, or more specifically, this is the additive conjunction if we care about linearity, or the negative conjunction if we care about polarity. And this is a tagged intersection, and it is defined by having two extractions, one for tau1 and one for tau2. And those are the left rules, and you can think of them intuitively as methods. And if we wanted to express a method invocation, again, we would have a cut between a producer and such a consumer, which is such a method. Now, the right introduction for this kind of conjunction is like an object, which is prepared to respond to both the first and the second extraction. Isn't this beautiful, right? Unfortunately, this is imaginary and not real. Okay, this is real. We have actual hardware, and we have registers that contain machine words, and we have memory that contains bytes, and we have code that contains a sequence of instructions. And here I was nice enough to render them in a human-readable form, but actually those are, of course, bytes as well, as we've just seen in the last talk. So how do we get some structure into this unstructured mess? Well, we do so with types. And so, for example, the parameter types of functions tell us what has to be in which register when we enter the function. And data types tell us the shape or the layout of memory, if we have pointers into those. And here we, of course, have a node of a binary tree that has two subtrees that, again, point into other pieces of memories. And the same invariants hold for those other pieces. Now, these algebraic data types, aka Rust-style enums, are very useful, and by now pretty much every language has them. What is less common are so-called co-data types, and intuitively they give structure to computation. So, for example, if we would explicitly pass an exception handler, this would be a pointer into code, and it would point to a vtable, let's say, with two methods. And then if we follow the second methods, it does a dispatch on the exception payload, which again then is a jump table. Now, after I've given you this intuition, let's look at a concrete example. Let's say we want to compile error handling code, and so we have a type of results that is either OK or an error, and then we have a function check that checks if the x is positive or not, and if it's positive, it's OK, and if it's not, then it's an error. And so in function main, we match on the result and then exit the program. This code like this is very common, and many languages have syntactic sugar for sequencing these kinds of matches. But if we would compile this naively, then the function check would allocate a constructor for OK or error, and then the function main would immediately match on this and destruct it. So in classical sequent calculus, we have two interesting ways to express this program. On the one hand, we can view the result as a positive type. And so in check, we receive a consumer, K, and in the then and else branch, in each of them, we have a cut between the consumer K and one of the two injections. Now, this is OK. In function main, what is a bit novel is that we can now directly pass the match. So we have a representation of the matching context, and we pass the match to a function check. On the other hand, a second way to express this program is with co-data types. And so we can employ something like a handler passing style, where the function check receives a handler and then invokes one of two methods on this handler, depending on if it wants to signal OK or an error. And in function main, we construct an object which then implements both of these methods appropriately. I've shown you now two ways to express the same program. And now, interestingly, and this is kind of the punchline, in our intermediate representation xcut, those are exactly the same. So we represent them in exactly the same way, and we generate exactly the same code for both of them. Namely, in the else branch, for example, we do an indirect jump to a vtable. And importantly, the payload, minus x, is in a register and stays in a register, and there is no allocation. And then on the other hand, in function main, we load the vtable into a register before we jump to check. OK, so the paper, in the paper, we present this intermediate representation, xcut, and it's quite a bit more general than what I've just demoed. And the paper is quite a bit more technical than what I've just shown. So of course, we have the syntax, and we have a formal definition of the typing rules. And then we have a very, very, very small step operational semantics that satisfies progress and preservations. And then inspired by this very small step operational semantics, we present code generation for our intermediate representation. And interestingly, the structural rule of exchange, for example, corresponds to parallel moves. And the structural rules of weakening and contraction correspond to memory management operations. And then we've implemented all of this, and we generate code not only for RISC-V, but also for x86 and for ARM. And we've run some benchmarks. And although we do not do any optimizations, these benchmarks show that the approach works, and it's not unfeasibly slow. And with this, I'm happy to take your questions.
If you have questions, please come up to the microphone.
Great talk. So do you support negation or classical double negation and continuations?
Yes. So the question, yes. A negation is definable as a type in the system itself. And so you can have an argument of a negation type. And this would correspond to the typical continuation we know from a continuation parsing style. And so the whole system is classical. And so, yes, we do support double negation, and we do support other related control operators.
Hi, Max New, University of Michigan. 2 questions. First of all, it's not linear, right? It's not classical linear logic? Okay, just to be clear. And the other thing was, you said that you had these 2 features, the dual features of each other, and they were compiled in the exact same way. So why not unify them in the source language if you're going to end up compiling them the same way anyway?
Good question. I want to have a comment on the first thing. It's not linear, but it's, let's say, linearity ready. So most rules are formulated in a linear or even ordered logic way. And then we have separate rules for weakening and contraction. And so you could just drop those or restrict those. And that's what we want to do in the future. And regarding the second question, yes, that would be super cool. But for, let's say, backwards compatibility with users' expectations, we so far haven't unified these data and codata types in the source language.
Well, I mean, they don't have to be unified in the source language, but I guess you could have another intermediate representation where you unify them and you translate from this language where they're different to one where they're the same.
That's what we do.
Oh, you do this?
Yes.
Oh, I see what you're saying.
Okay, yes, yes, that's what we do.
Okay.
Sorry, I misunderstood your question. Okay, I thought as a user-facing, but that would be very confusing,
sure.
right?
Okay, yeah, thank you.
Any other questions? If not, then thanks again.